Okay, let's look at this one. So, with absolute values, anytime we've had absolute value, I've talked about this a few times, and I know we've had to do it once or twice so far. It will become second nature because we'll do it every time all year long. I can't do anything with an absolute value when it's written this way. What do I have to do instead? What did we change it to?
Absolute value run the whole thing.
Remember we had to write it without an absolute value function?
What?
Yeah, I don't know.
So we used the piecewise definition for absolute value?
Like one where it's equals 0 and one equals like negative, whatever.
Yes. So we will do this every single time we see an absolute value, but an absolute value has a piecewise. It does, if you put in a positive, it doesn't change it. So you get out x if your x is greater than 0. If you put in a negative, it gives you the opposite. So it gives you a negative x if x is less than 0. Now 0 could really fit with either of these, couldn't it? Like, if you put in 0, you get out 0, and 0 is the same as the opposite of 0. So technically I could put an equal to on either one of these. I'm not going to put it on there right now because a limit, we don't care what happens at 0, we care as we approach it. So really this is all we need. So we're going to do the limit as x approaches 0 of this piecewise function.
I thought absolute value was always positive.
Right. So it's saying if you put in a negative number like -4, it does the opposite of -4. And the opposite of a negative makes it positive.
So why does it say that if x is less than 0, it's negative?
Okay.
So if it was negative, you'd plug it in, and then it'd be a negative and a negative, and they would just cancel.
So if I put in a
So I'm going
negative,
to say it's always positive because I don't
well,
understand that.
yes, but we're going to have to use this. Like you're going to.
So I need to understand
Yes.
it. Yeah, then
So
I need to explain
what
it.
we're saying is if I put in like a +2, I get out 2. So I get out what I put in. Okay, so when I put in -2, I need a way to say you get out the positive. So what I said is you get the opposite of what you put in because 2 negatives make a positive.
Okay.
So if x is a negative number, we do the opposite of it. Opposite of a negative is positive.
Because to me it just makes sense if you say x if x is greater than 0 and then x if x is less than 0.
But
It's
that,
the same thing.
well, if you said you get out x when x is less than 0, that means if I put in -5, you're telling me I get out -5.
No, you're going to be at +5. In my brain it makes sense. Can I write it down the way that it makes, because this does not make no sense to me.
No, we're going to have to use this, like this
Oh
definition
my
here.
gosh, this makes no sense.
You're wanting to think of it,
It's like that negative is already there, and then you put another negative inside
Right.
the negative, so it cancels it out.
you're reading this differently. When you see this, you're thinking -x. Try not to think of it as -x. Think of it as the opposite of x. So if x is a negative, we do the opposite of a negative, which is positive. And we will do a lot more with the absolute values, so this isn't a one and done thing. We'll see this a lot. All right, so we've said sometimes you can plug it in, sometimes we can't. We don't really know for piecewise definitions. We haven't looked at any piecewise functions yet. So let's look at the left and the right and see what happens. Because we know if the left and right hand limits match, then we get the same thing. We get the two-sided limit. So if you are approaching from the left, okay, of the absolute value function, which of these two pieces would you be on? If the top. So that would just be x. And so if you're approaching 0 of just x, we would get 0. Right? if you're approaching 0 from the left of the absolute value? Which piece are you on if you're approaching 0 from the left? The first or the second? The second, because we're putting in negatives. So you're getting out the opposite of what you put in. Okay, but this is just like a polynomial, and we know we can plug those in. So if we plug in a 0, we get the opposite of 0, which is 0. These things are equal. If the left and right hand limits are equal, that means the two-sided limit works. So the limit as we approach 0 of the absolute value is in fact 0. And the reason I had to go through all this is because I don't have a limit law yet that tells me I can just plug in something inside an absolute value. Okay, so that's what we're working towards. We're trying to figure out, when do things work as we expect them to? Did this work out as we expected, where we could have just plugged in the 0? Yeah, that one did. Let's look at another one and see what happens. Okay, so I'm going to see, and I'm telling you to prove it doesn't exist. So I'm already telling you that this limit doesn't exist. We want to figure out why. So, my goal, whenever we have absolute values, we are going to have to think of it as a piecewise. Okay, so we'll have to rewrite this. So when I have the absolute value of x over x, I need to figure out what that equals if x is greater than 0 and if x is less than 0. Can you plug 0 in there? No, x can't equal 0 on this one. It does not exist. Okay, so if I plug in something greater than 0, so if I put in a 1, it gives me the absolute value of 1 over 1. If I put in a 2, I get the absolute value of 2 over 2. If I put in a 3, I get the absolute value of 3 over 3. What are all these things turning into? 1. Okay, if I put in a positive, the top and the bottom are the same, so we just get out 1. All right, if I put in a negative, so if I said the absolute value of -1 divided by -1, so that becomes 1 over -1, which is, if I put in -2, I get a positive 2 on top and -2 on the bottom. So if we put in negatives, what do we get out every time? -1. Okay, so if I'm trying to figure out this limit, let's do it from the left and the right. So if I did it from the right, which piece am I using if I approach from the right? The top. So that's saying the limit as x approaches 0 from the right of 1. And we know from Friday, limit of a constant is the constant, so that's equal to 1. As we approach from the left. So we're plugging in things smaller than 0, so which piece are we on? The bottom. And we said the bottom one's equal to -1. So the limit as x approaches 0 from the left of -1 is -1. These are not equal. So what does that tell me about the two-sided limit? We can do one-sided limits, but not the two-sided here. Because they have to match up. Since the left and right take me to different numbers, we cannot do the two-sided. Okay. I want you guys to see if you can figure out if there's a limit as x approaches 4 of this function. So it's a piecewise function. You need to figure out the limit as we approach 4 from the right and the left and see if there would be an overall limit. If you're approaching from the right, that's things bigger than 4, so you're on the first piece. So we have the limit as x approaches 4 from the right of the square root of x minus 4. We have a limit rule that says you can just plug in under square root. When you plug in that number, the limit goes away because we are evaluating it. So we get the square root of 0, which is 0. Okay, if we're approaching from the left, so we're plugging in things smaller than 4, so that's 8 minus 2x. But if it's a polynomial, we know we can just plug in. So we have 8 minus 2 times 4. So 8 minus 8 is 0. So these are equal. So that means the two-sided limit does in fact exist. And it is 0. Yes, Bob?
So why did you not well, before you said if it was like 2x, you would bring the 2 to the other side of the limit, right? So
Yes. I'm just showing less of that. So, yes, our original limit law said you take the limit of each term, and then if you have a coefficient, that can be pulled out in front, and so forth. But then at the end of our lesson, or close to the end, we had the direct substitution property. I don't remember where that was. So it was like before example 3 in the notes, and it basically said if it's a polynomial or a rational function, you can just go ahead and plug in the number. You don't have to show me every little step along the way.
okay.
All right. What's this? Huh?
I don't know what that means.
What does that thing mean?
I knew you were gonna ask
Value,
that.
the absolute value.
Algebra 2, we did it for a day
It's been a long
in college
time.
algebra. C starts with a G. Greatest
Common factor.
integer
That's
function.
actually
I never would have got that. I don't even know what that means.
That's the step function. So greatest integer function, you can't get out, you only get out integers, and you can't get out anything bigger than what you put in. So if you put in 0, you get out 0. But if I put in a half, we're still getting out 0. If I put in 3/4, we're still getting out 0. But what happens when you plug in 1? Yeah, you get 1 out. So we showed that with a step. It ended with an open circle. So this was our step function.
Oh.
Yeah, it's been a bit, but we have seen it. And remember, these steps just keep going forever. So since we already have the graph here, let's just use this graph. As you're approaching 3. So let's see if it exists. As I approach 3 from the right. Okay. So here's where x is 3. If I'm approaching this from the right, I'm putting in things bigger than 3. So 3.5, 3.4, 3.2, 3.1. What am I getting out? 3. If I approach 3 from the left, I'm putting in things smaller than 3. So I'm putting in 2.5, 2.7, 2.9. What am I getting out? 2. So, does not exist. All right. I am going to cover one more thing today. So this last rule is a little more abstract because sometimes we can't just evaluate the limit. There are certain things we don't have any limit rules about, like trig functions. Do I have a rule that says if you're doing the limit of a sine x, you can just plug in x? No, we don't have that. So because of these weird functions, there is something called the squeeze theorem that we will use. We are using that very minimally this year. In other words, this year I am showing it to you. We'll do a couple problems, but all the problems we're going to use it for are going to be essentially the same.
Now, if you can take college.
If you have to go on to take, Calc 3, you might see this come back. So that's why I'm not just going to skip it. Like in Calc 1, it's really not necessary for a lot of things we do. But in higher levels of Calc, it can come back. So I can't skip it. We have to see it and have an understanding of what it does. So the squeeze theorem is something you can use if you're trying to find the limit of a function that we can't work with. And the idea is if you've got some function here, let's say, all right, I need the limit of this function. And maybe I can take two functions that I do know. So maybe I want the limit right here. This is my point of interest. I want to know what the limit is right there. Okay, maybe I can't figure it out because I don't know enough about that function. But if I could compare it, if I knew that there was one function that was always smaller or always bigger than that one, and I knew another function was always smaller than that one, then if those two had the same limit, the one sandwiched between them would be equal to the same thing. So that's the idea we're going to do. We're going to take two functions that we do know, that we can squeeze this in between, and use those limits to help us. All right. So that's what this tells us. If you know that one function is always smaller than another, then the limit will always be smaller than the other. And the squeeze theorem says if you have three functions where one is always less than or equal to the middle, which is less than or equal to the biggest, and if the limits of these outside two are the same, then that means the inside one equals that number as well. So there's a picture of what I was already describing. We are going to use it for this function. So we have absolutely nothing that tells us that this limit should equal 0. I'm telling you the answer is 0, but could I have just plugged in a 0 there? No. First of all, I don't even know if I can bring it inside a trig function. Second of all, it's 1 over 0 inside the trig function, so we couldn't do that anyway. But let's start. All the problems we're going to do it with are going to be sine and cosine problems, because sine and cosine always fall between what two numbers? 1 and -1. So it starts off with a very basic inequality that we know. So we know that -1 is less than or equal to sine x is less than or equal to 1. You notice I'm not just jumping straight to this middle thing. We have to work our way up there. Now, if you're taking sine of something, when you mess with that angle, does it change the high and low points on the graph? No. Remember, the only thing that changes that was the amplitude, the number out in front of sine. Changing the argument just changed how quickly it repeated. So I want this to be a 1 over x. Is it still true that sine of 1 over x would fall between -1 and 1? Yeah, because no matter what my angle is, the amplitude won't change. So my next step and I'm picking that just because my angle is 1 over x. If this angle were 3x, then I would have made that a 3x there. Now, I can't just throw an x squared out in front and assume it's still going to be between -1 and 1, because the coefficient changes the height of our graph. But x squared is a positive number, right? So would it be legal to multiply all of these by x squared? It won't flip my inequalities because it's still positive. So I'm going to take everything here times x squared. So that means negative x squared is less than or equal to x squared sine 1 over x is less than or equal to x squared. Have I lost anybody? So, look back at what we're going for. We have the x squared sine of 1 over x. What's the other thing we need? Limit. We are going to do the limit of all three pieces because we have a theorem that says, well, if this inequality is true, then we can do it with the limits as well. So I'm going to add a limit as x approaches 0 on each of these pieces. But we are in really, really good shape now. Can you do the limit as x approaches 0 of negative x squared? Yeah, that's polynomial. You plug in the 0. What's the opposite of 0 squared? 0. It's less than or equal to the limit as x approaches 0 of the x squared sine 1 over x. It's less than or equal to, what's the limit as x approaches 0 of x squared? 0. So this limit falls between 0 and 0, so the only option is
0.
it equals 0. If you had done it and got that it was between -1 and 3, would that have helped me? No, this only works when these final two numbers are the same. That's when you know that the middle limit has to be equal to those. So again, for now, I am going to be, well, not just for now. When we do the squeeze theorem, I'm going to be very deliberate about the examples that we pick. We're really going to stick with trig functions, sine and cosine, so that we can always start out with the fact that they are between -1 and 1. Because we're really just trying to understand the idea of what it does. There's not a lot that we really are going to have to apply that to this year. Do you guys think you could do it on your own? Where is your optimism? What would my first statement be? Because we can't just plug in. We don't know that that's legal with the trig function. We're talking about sine, so we'd have to say -1 less than or equal to sine x less than or equal to 1. We're always starting at the ground floor, the -1 and 1. Then I have to manipulate this. So what's the next thing we need? The pi x. So we can just change that. We know we can change the angle and it does not change my -1 and 1. What's the next thing we need?
Yes.
So how do we get that in there?
You just put it in.
You take everything times x squared. Since that's a positive number, the inequality doesn't change. Okay, so I have the x squared sine of pi x. What do we need now? To add a limit to every piece. approaches 0 of negative x squared is 0. We can't work out the middle. And the other one is also equal to so this limit equals. Last problem. Isn't that pretty?
No.
What's the first step? -1 less than or equal to sine x less than or equal to 1. What's the next step? Right. We can change the angle to the 2 over x. Okay, so I've got this much. Now what do we need?
Square root of x plus x squared.
Yeah. A square root is a positive, so we can just take everything times that. So I would get a negative square root of x plus x squared. Less than or equal to square root of x plus x squared times 2 over x. Less than or equal to square root of x plus x squared. What's the next thing I need? Plus 1. And if you add 1 to each piece of the inequality, that's legal. So we can just tack a plus 1 on the end of everything. Alright, we're almost there. Now what? A limit. You do have to show this much work on these. I know it's annoying, but this is like a proof, proving something, so you have to be able to justify every step, and you do that by showing your work to justify every step. So I don't often make you show me everything, but this is one of those where you have to show me everything, because your answer is this, not just the final number. Okay, but we know that we can plug in the 0 under a square root, so we get a negative square root of 0 plus 1, so that gives me 1. Less than or equal to, I am going to cheat and just draw an arrow and show that's coming down. Less than or equal to, if I plug it in over here, we get the square root of 0 plus 1, which is 1. So, this thing equals 1. So here's the game plan. There are book problems on this. Those book problems are not due until Wednesday. Tomorrow is a work day. But I have posted a handout on Classroom. This handout is more like the one you turned in today, so it's 8 questions, more just your basics. So there's no squeeze theorem or piecewise functions or anything like that. It's basically practicing when you can plug in. Remember, if you're plugging in and you get 0 on the bottom, you need to factor and reduce first before you plug in. So it's more the basic problems. I want you to work on those.